And so the next speaker is Manjula, and she will be talking about improved multivariate analysis data products for ARM mass spectrometer datasets.
So I'd like to thank the organizers for letting me join in and tell you a little bit about the work that I'm doing right now. I don't normally attend this workshop because I haven't really worked with machine language or AI issues before, but right now we have some data analysis needs for large mass spec data sets that we think could learn from the work that this community is doing. So in addition to me, we have my co-authors here on this work, Jose Jimenez and Davin Henser from CU Boulder, Doug Borsnop from Aerodyne Research, and Pentti Paatero, who's retired from the University of Helsinki in Finland. Okay, so we haven't heard much about mass spectrometers today yet, so I thought I'd give a quick overview about how mass spectrometers are being used to learn more about atmospheric chemistry. So is this in the way? Let me just get rid of this actually. Okay. So mass measurements are increasingly being used, over the last 20 years really, to provide real-time chemical composition and concentration information about gas and aerosol phase species that are in the atmosphere. And if we're talking about aerosols, for example, if we want to try to understand their radiative effects or health effects, we need to know something about the chemical composition of these particles. And the mass spectrometers that have been used most often for these are aerosol mass spectrometers, such as the aerosol mass spectrometer, which is a research grade instrument, and the aerosol chemical speciation monitor, or ACSM, which is a instrument that is based off the AMS, but is more amenable to long-term routine monitoring. So in addition to aerosols, we also, of course, want to know about the gas-based species that are emitted into the atmosphere and are transformed through oxidation to form semi-volatile species that can condense to form aerosols. So we're talking really about a continuum of species in the gas phase. And for these, in recent years, chemical ionization mass spectrometers have been used. And they are allowing us, again, to learn more about the chemical composition at molecular level for the gas phase and even the aerosol phase species that are present in the atmosphere. So here I'm showing you an aerosol mass spectrometry global database. This was actually put together by Chi Zhang and coworkers with funding from DOE to try to collect in one place some of the information that has been obtained from, in this case, aerosol mass spectrometers around the world. And the purpose of this slide really is to show you how widespread the use of aerosol mass spectrometers has been. You can see they've been deployed in many fixed sites, urban downwind, and rural remote, and as well as in many aircraft missions as well. So the data analysis needs that are that I'm going to present to you are really important for a large set of measurements around the world. Of course, some of the flags shown here actually belong to ARM mass spectrometer data sets. So ARM actually has long-term measurements from DOE's ACSMs. DOE owns 4 ACSMs, and they have been deployed at the SGP site and the ENA site, as well as aboard the on the AMF1 and AMF2 instrument deployments. In addition, in terms of deployments, it's also been field campaign intensive operating period deployments that have provided both AMS and SIMS data sets from guest instruments that are not part of DOE's ACSMs. This includes fixed site and aircraft measurement campaigns like Milagro, CARES, Bebop, High Scale, and Go Amazon. And of course, we expect more. There are ongoing measurements or planned measurements, as well as future field campaigns, which could include mass spectrometers on board the new ARM aerial platform as well. So again, the improved analysis methods I'm going to tell you about, or that we need, are important for increasing information from all of these mass spectrometer data sets, including what ARM has now and also in the future. So mass spec analysis, as far as we are concerned, involves analyzing these data matrices that consist of mass spectra as a function of time. So blow this up a little bit so you can see what a mass spectrum looks like. This happens to be an aerosol mass spectrum from the ACSM. So you have ion intensity versus ion mass charge. And this is a unit mass resolution spectrum. But if you are working with a high resolution mass spectrometer, you can get within this unit mass, you can actually separate out the many ion contributions that are also present at the same time. So depending on the mass spectrometer that is used, you can have many, many ions and high resolution information. So typically one can actually identify some key species like ammonium, nitrate, sulfate, and chloride in an aerosol mass spectrum. But there are a lot of these green ions here that are shown that are not just simply identifiable right away. And for this, we use multivariate analysis, where we analyze the entire mass spectrum rather than a few selected ions. And we try to find the chemical compositions and concentrations of the distant groups of ions that correlate with each other. And the goal here is to use this to get insights into the sources, processes, and the effects that these aerosols can have. So the technique that we use for this is positive matrix factorization, in which you have a data matrix, which is expressed in terms of the sum of factor matrices and a residual matrix. The goal, of course, is to have small residuals and have this entire sum reproduce the original data matrix as well as possible. The user can control the number of factors that are used to reproduce this data matrix. So PMF has turned out to be one of the really the best methods for us to use, because it allows us to get interpretable and useful information for source apportionment and model constraints. Particularly useful for PMF, or the reason why PMF is useful, is that it allows us to obtain positive elements. It allows us to not use a priori information, and also we can weight the points by their uncertainty. So I'm going to skip right on here because it looks like I don't have a lot of time, and I want to tell you a little bit about the challenges that we have with current PMF analysis. The main challenges are that they are too slow for the large data sets that we have, which are greater than 10 to the 6 data points. So, and also on top of that, the users have to choose the optimum number of factors, and this can take time. So when I'm talking about large mass spec matrices, I'm talking about things like greater than 10 to the 6 elements, where which are just really very easily attainable when you operate these instruments. For example, an ACSM in 5 months attains these sizes. Fixed site HR TOF AMS achieves these sizes in 1 month. Airborne HR TOF AMS achieves it in less than 1 day, and a SIMS in less than hours. So this is an issue, and when you analyze these matrices, you are spending a lot of time. So for example, the HR TOF AMS measurements take about 1 day to analyze 1 flight with PMF. So if you want to analyze many flights together, this is really untenable. So in this example shown here, 21 flights were taken together, and you could not analyze that with a PMF analysis without averaging all the data down to 1 minute, which means that you drastically reduce the spatial resolution from 175 meters to 10 kilometers, which basically means you couldn't get plumes or resolve plumes, biomass burning plumes, for example. So this is an issue that the only way we can really do PMF analysis is average down in time or mass resolution or spatial resolution. So our limits to the information that we get now are not the mass spectrometers as much as the analysis methods. So we need faster, more efficient, and more automated analysis methods for these large data sets, including the ARM mass spec data sets. A key, of course, is that the information that we get has to be interpretable, and has to be something that we can use to understand the sources and processes that are that are contributing to the aerosols or gas phase species that are measured, and then can be used as inputs or constraints in models. So ideas that we have for improved multivariate mass spec analysis include potentially efficient PMF parallel processing, where instead of having kind of a large X matrix that is factored into G and F, we break up the X matrix into many blocks and then do the processing in parallel, so that then we can get some more information. We also are considering two-step processes in which we first compress the large data set with methods such as FFT or SVD, and then run PMF on the compressed data set. So this is possible because in typical mass spec matrices, the information is actually sparse. So even though you have, thousands of ions or hundreds of ions, out of them only about 10 to 30 factors, which are the groups of ions that covary, are required to explain the original data matrix. So we think that this might be a very promising method, and initial tests are suggesting that speeds can be made faster by about a factor of 10. Of course, there's potentially a lot of use for machine learning in this process. It could help with the automation and the rest of this process as well. We are looking to learn from this community and see how these kind of methods can be used to address this problem. So to conclude, mass spec data sets are increasingly important to ARM, especially to obtain chemical information about gases and particles. Current mass spec data analysis is limited because of the efficiency and the speed of the techniques. So we want to learn from techniques used by other communities for big data. And if we want to really talk about, oh boy. Okay, and if we want to talk about the kind of new analyses that we can do with the with this kind of improved efficiency PMFs, we could do long-term analysis. So, many more than 5 months of ACSM data. We could do multi-year, multi-season analyses. We could do aircraft measurements where instead of only limiting to one flight or averaged flight data, we could do over many flights together so that we could try to find commonalities. We could do integrated multi-instrument analysis, which I didn't get to talk about because I was worried about running out of time. But basically, in addition to the mass spectrometers, we could combine data from other instruments like cloud condensation nuclei instruments or number distribution instruments, and in that way get more information about how the composition is affecting radiative properties. And also we could do combined analyses of mass spec data from multiple sites. So we think that this would really is important work that needs to be done. We would love to get some funding to do this type of work, and feedback and ideas, of course, welcome, especially from this community. And thank you for your attention.
Thank you, Manjula. So we still have over a minute left. So let's see if there are any questions from the group. So before that, I did have a question for you. You mentioned that, you mentioned SIMS data initially and some of the aircraft data at 1 second time resolution, but then the sensitivity also starts playing a role, right? So compared to like 1 minute or 2 minute data stream where you allow the instrument, a one second data quality may not be as sensitive. So do you have any comments about that?
Yeah, so in terms of the SIMS sensitivities are quite high. They can measure species down to PPT levels. Okay. And so they have been operated on aircraft and measure at 1 second timescales. And the key is that if you do that, for example, in the FireX measurements, they have operated an easy SIMS in that way and been able to get to actually resolve measurements within the plume of a biomass burning plume. So yes, it does have the sensitivity. Obviously, it depends on the environment as well. But
Okay. So I'm looking if there are any more questions here from the panel.
There's one in Q&A.
Okay. I cannot. Can you read it out? Because
Sure.
I cannot locate it.
For mass spectrofactorization, has hierarchical clustering of ion time series been considered? Is the tendency of PMF to split ions between factors considered a positive or a negative?
Yeah, so it has been considered, and it has been actually shown to be useful for some lab experiments, you know, where you factor for a couple hours of data within a lab, a smog chamber experiment. But in general, for ambient data, I think it's not going to be that great because you have to separate contributions for a single ion. Most of the time, a single ion has many contributions from different factors, and you can't do that within the clustering regime. I think the reason why it worked quite well in the smog chamber experiment was that you were having a continuously evolving system in which it was able to kind of separate out the evolution in terms of clusters, because a model like PMF actually assumes kind of that you can explain the final result in terms of constant factors, you know, contributions from different constant factors. And in a smog chamber experiment where you're having huge variation on short time scales, the clustering seems to do a better job. But in ambient situations, it seems that because there is really a need to apportion a given ion to multiple factors, it won't be as good.
Yeah, I have a follow-up comment. So if you have aircraft measurements where the aircraft is rapidly encountering different types of plumes, maybe there is still a hope for clustering methods there.
Yes, yeah, and it could be a combination. You know, there might be a way in which you do some kind of combined clustering slash PMF type method, you know, where maybe you even use plumes to give you an idea of what certain factors look like. And then that transfers into not necessarily PMF, but multilinear engine, which allows you to kind of give an a priori knowledge of certain factors. And so you could do those kind of things as well. The issue, of course, will always be that these techniques, these particular techniques are slow.
Yeah,
for
I
large
just
data sets.
mentioned because we are exploring some clustering techniques in our group also, in addition to, and then we are also combining with some climate model predictions to get more insights about variability of data. So,
Yeah, I'd love to chat more about that, but with you.